Lawrence, are you going to let me share?
Yes. Okay, why don't we go ahead and get started? Our speaker for today is Trevor Sewell, and he and I have been friends for, I don't know, a long time. Actually, I talk to him several times a week. I did not prepare an introduction for this talk, but if you got the invitation, you can read his bio sketch. One thing I guess I'll mention is he has been working on enzymes that are involved in that are useful in industrial biotechnology. A class of enzymes called nitrolases, which he may or may not talk about today, and also a class of enzymes that are important in the tuberculosis life cycle. So, and there's a blog post that I can put into chat on that. He may or may not talk about that today. I think he was a principal investigator for something called the START project that graduated a number of PhD students from University of Cape Town in structural biology and material science. So without further ado, I'll just let him get into it and give us talk today. Trevor, go ahead. Let me start.
Okay, thank you very much, Lawrence. That was very flattering. I'm not going to talk about the TV stuff, but I will talk about other things. Okay, so the main thing that I'm going to start with is the survey that we did under the auspices of the African Strategy uh, for Fundamental and Applied Physics, which was a huge project ultimately sponsored by UNESCO. And and it was a survey of all physics in Africa. And not everybody in all the disciplines of physics participated, but the biophysicists did. And now, how do I change slides? Oh, Lord. Um, Lawrence, you got to help me.
I just use the arrow button on my keyboard,
Um,
or I just
somehow,
keep hitting every button until something happens.
uh, this is not going to be useful. Okay, that changed. Okay, so slideshow. Okay, so that one is active. Can you see it's not in presenter mode?
It's not in
And
presenter mode.
yes, if I now go slideshow, play from start. And now, goes. Okay. So this is the summary of what we concluded from the ASVAB project. And we saw that there were a number of challenges in African biophysics. The main is that there's a lack of basic and advanced equipment. There's a lack of funding to maintain equipment. This has a consequence that people are not really prepared to invest in infrastructure in Africa. Furthermore, there's a very low critical mass of biophysicists in Africa. This means that people, especially young people at the universities, are not aware of the field, and those that become aware of the field leave Africa and go and work abroad. The other consequence of all of this is that there are very few people to mentor the young people. So they look abroad for mentorship, and then ultimately they're attracted abroad. So what we do think we need is capacity building, and we need educational curricula that will build our capacity. We need mentorship, we need public awareness, and we also need some mechanism for retaining the people that we train. And that could be spin-out companies, but it also could be extra posts at the universities and at the moment, I think biophysics should be university-driven, and probably people are not going to make a profit out of it at the moment. So I think that hoping for spin-out companies is far-fetched. So what we do need is infrastructure, and that means that we need to buy equipment, and we need to set up an infrastructure that will help us to maintain that equipment so that we can keep the show on the road. And this can potentially be done by low-cost innovation. So Africans can, in fact, use manufacturing techniques to make things themselves, so that we can, in fact, develop some aspects of the biophysics industry locally. So we have fairly widespread agreement on what the problems are. Let's see if we can think through ways of solving them. Now my key doesn't work again. There we are. Okay. Okay. So what our report discovered that there were fewer than 100 Africans who work in Africa who self-identified as biophysicists and structural biologists. The structural biology equipment in Africa is almost all in South Africa. So in Africa, there are 4 protein-capable rotating and X-ray diffractometers. There is one 30-year-old cryo-FEG-TEM, which is in Cape Town. There are no FEG-SEMs or dual beam instruments for making lamellae from biological specimens. There is one native protein mass spectrometer. There is one greater than 600 megahertz NMR for protein work in Cape Town. And we have many high-end light microscopes, but they're also mostly in the Cape Town area. There are a number of people that have tried to start activities to build up the core biophysicists, and among these, and one of the most important ones is BioStruct Africa, who's had a great deal of success in the rest of Africa, outside of South Africa, in building up some enthusiasm about structural biology. We have in Cape Town, had a project on teaching people about cryo-electron microscopy through the CZI program. And this has involved both cryo-EM and light microscopy. We've had at UCT a relationship with
biology and drug discovery across Southern Africa.
Google is talking to me. Okay, so we have developed a relationship with Instruct Eric, and I hope that we'll be able to expand this relationship shortly, because we've applied to Horizon for funding to expand that relationship. We have these monthly meetings, and we have a number of ad hoc meetings by prominent Google seems to insist that it needs to talk to me. Okay. Okay, we have developed a number of block allocation groups at Diamond Light Source, at EBIC, and at ESRF. And we have an MOU with Instruct Eric that enables our young people from the University of Cape Town to do some work overseas. And many South African universities have awarded PhDs in structural biology, 7 of them, in fact. Now, our first venture into the outside world actually was with the ESRF, and in 2003 we gained access to the ESRF as a result of an MOU with EMBL, who operated the beamline BM14. And this led eventually to South Africa becoming a subscriber to the ESRF. And on 21st of May 2013, South Africa took a 0.3% subscription in the ESRF, which enables all scientists in South Africa to use any of the beamlines at ESRF, including the electron microscopes. So this has been a huge bonus for structural biologists in Africa, but it has been a disappointment in that it hasn't been used as much as one would hope. So the pressure from internally to make use of this resource has not actually justified in the eyes of the NRF, who's paying for it, the value of the subscription. What we did in Cape Town starting in the year 2000 was to plan a facility which ultimately we called the Aaron Klug Center for Imaging and Analysis. And the purpose was to provide the instrumental resources and expertise for structural analysis in all disciplines, including structural biology. And we built a new building eventually, which was completed in about 2012, which is this blue building over here. And in this is a very special building. I'll show you. It was designed for high-end cryo-electron microscopes. It was 660 square meters, vibration-free, magnetic field compensated, temperature-controlled, humidity-controlled environment. And we plan to put in 3 TEMs, 4 SEMs, a protein diffractometer, preparative equipment, and computer infrastructure. So at the moment, we're trying to buy a modern cryo-TEM, a Glacios 3, which I'll talk about a little bit further on. And the Gates Foundation has awarded 2/3 of the cost, provided UCT can raise the remaining funds. We will then have automated acquisition systems, web-based image processing interfaces, and we are hoping for integration with the national high-performance computing systems so that we can engage in international networking, computing, and storage. What we have at the moment, is a lab which enables us to prepare proteins as well, and this is absolutely essential. So we have chromatography, we have facilities for crystal trials, and we have obviously the facilities for X-ray diffractometry, which are getting a bit old at the moment, and I'll return to this later. A huge development that occurred in between 2018 and 2022 was the START program, of which I was the structural biology lead. And that created a UK-Africa partnership to develop a program of world-class research, including in structural biology, but based at the diamond synchrotron. And from our point of view, this provided us with facilities for X-ray crystallography that we'd never had before. It provided us a resource, the expertise that was at Diamond, and it provided us ready access to the Cryos electron microscopes. And as a result, one of our graduates, Jason van Rooyen here, became the head of industrial electron microscopy at Diamond, and that has made life quite easy for us to gain access and to maintain access with the Diamond light source. So the way that we operated with using the facilities at the Diamond light source was that we prepared the protein and optimized it in our own laboratories. We then looked at the protein by negative stain microscopy. We then developed the microscopy to a level where we thought it was going to be suitable for cryomicroscopy. And then we prepared the cryo grids, shipped them to the Diamond facility, and collected data on the Cryos instruments, and then shipped the data back to South Africa for processing. And as a result, we did quite a lot of structures. In the end, there were about 30 papers and about 60 deposited structures. And I'm going to talk a little bit about one of the deposited structures, which was the structure of angiotensin converting enzyme. So what I think the main achievement was that we established a mechanism to enable more people to become involved by giving people free access to the resources of the Aaron Cook Center, and also by holding workshops, and that eventually led to people making use of the Diamond facility. One of the problems that we continue to face is that South African funding remains very limited, but it certainly has helped in critical areas. The largest threat that we face is the loss of members of our very small community. This means that it's imperative to find sustainable funding to retain the people that we train. Now, back to angiotensin converting enzyme. This project started as a crystallography project. Ed Starrick's lab discovered that if you mutated the residues to which the sugars were attached, you could make crystals of the protein. And as a result, we solved several crystal structures in complex with various different drug complexes. And one of the investigators, the young people that were involved in this, was our student Jean Watermeyer. And later on, Jeremy Woodward also became involved in the electron microscopy. So angiotensin converting enzyme is a protein that maintains the concentration of angiotensin, which is a peptide that controls the blood pressure. And it's extremely relevant in Africa because cardiac disease is extremely prevalent in Africa and is a major killer of people. So what happens is that the enzyme is made up of two very similar lobes that are connected by some sort of flexible linker. So you can easily express either one of these domains independently, and you can deglycosylate these by mutation, and then you can crystallize. So in the end, we have crystallized both the N and the C domains. So we have various structures, and we have examined this in some detail, and I'll get back to this in a moment. But the important one for our purposes is this C-terminal domain. And one of the problems is that the active site's very similar, and you want to only inhibit the C-terminal domain. So we've tried to make specific C-terminal domain inhibitors and inhibit the conversion of angiotensin 1 to angiotensin 2. And that has been more or less successful. But eventually, we decided that we would, okay, let me talk about this. It was discovered by Ed Starrick and his co-workers that an important state involved the dimerization of the angiotensin. So an angiotensin monomer consists of the N and C terminal domains and this transmembrane component. There is some, if you design a biofluorescent complementation probe, you can see that dimerization does occur in the cell. And so some efforts were made in order to predict the structure of the dimer using Sachs. And this was the published Sachs structure of the dimer of angiotensin. Of angiotensin converting enzyme. And so at that stage, the effect of the dimerization was completely unclear. And so that was one of the problems that we hoped to solve by the cryo-electron microscopy. So what we did was that we would try and take the fully glycosylated monomer without the membrane-associated tail and get a structure of that by cryo-EM. And so what we did eventually was we took 7,700 micrographs approximately on the Titan cryos at Diamond with the K3 detector. And then we did a whole lot of auto picking, 2D classification, 3D refinement, and we eventually got some sort of monomer structure, which you can see here. But during lockdown, Lizelle and I were listening to an online seminar, and we listened to Tristan Beppler. And he had recently written, he'd written a positive unlabeled convolutional neural network for particle picking and cryo-electron microscopy. And this developed into an extremely powerful tool, and we used it to actually get much better images, and also images of the multiple states of the enzyme, which I'm going to show you, and indeed the dimer. So we were able to use this program called Topaz and train it to recognize monomers and dimers and the multiple states of both of those. And then we reconstructed everything using the CryoSpark heterogeneous refinement system. Now, it must be said that it was an extremely challenging project. The identification of the particles on the micrographs was very difficult because the protein had a very low signal-to-noise ratio due to its small size. The protein domains are globular and often resemble noise at close to focus. And the monomer views were ambiguous. The size of the orthogonal monomer projections showed very large disparity. and the signal to noise ratio was low, especially for the monomer top view. The dimer showed high flexibility and thus was very difficult to align. So none of these things could have been achieved without the Topaz learning program. So here are our post-Topaz reconstructions. So this is the monomer, and you can see that the glycans are all N-linked, and they're shown in green. So you can see there are many glycans, and as I said, all of these were cut off in the crystal structures. So we were able to see now the complete, fully glycosylated angiotensin converting enzyme. And then we did, I'm going to show you in more detail, the 3D variability analysis. Now, as a result of our crystallographic studies, we'd identified, and indeed our molecular dynamic studies, about 12 papers worth of studies, actually. We'd identified various hinge regions. We'd postulated that the dynamics of the molecule determined the binding to the different drugs rather than the static associations. And we had developed various models for how it might work, but nothing really prepared us for what we actually saw in the microscope. So let me show you first oh no, this is supposed to be a video. Okay, the video comes later. Nothing prepared us for what we saw. What we eventually saw was a dimer that looked like this. You can, if you remember what I showed you from the sacs, it's completely different. You can see that there's a side-to-side association of the N-terminal domain. And you can see in the cryo-electron microscopy studies, you can see the details of this association. And this is what the map looked like. You can see it's actually a very good map, in spite of the small size of the enzyme. And we were able to work out the details of the interactions between the N-terminal domain that resulted in the dimerization. And this, I think, is the major achievement of our paper. But there are others. Okay, so now, I hope I can, don't know why I can't show you the videos. Okay. So what we saw was that the C domain, which is this bit down here, was actually very ill-defined in the reconstructions, and we could see it was very mobile. Okay, so let's hope that this video shows. Oh, no, this is impossible. I don't know why I can't show you this. Oh, there we go. Okay, so for some reason I had to press that button. Okay, so if you analyzed all of the different images that we had and strung them together as videos, you can see the modes of vibration of the molecules. Let me show you again. Okay, now that's just that. Okay, and then we interpreted them in this way. So you can see that there are many modes of vibration, some of which involve movement around the central hinge, and others in which involve movement around within the lobes themselves. So what we'd done previously, and which we confirmed by the cryo-EM, is that there were several opening and closing modes where the active site, which is down the middle of this cleft, opened and closed and resulted in the cleavage of the angiotensin converting enzyme. And the most interesting thing about this is that the interactions with the various substrates depended not so much on the static interactions, but on the dynamic interactions. And these dynamic interactions were different in the N and C domains. One of the things that, oops, no, back again. No, why did I not get the thing? No, no. Okay, maybe I just gotta wait. No. Oh, that seemed to come up. Okay, so this shows you the dimer modes. Okay, and what you can see in particular is that the N terminal, when the dimer is formed, the N terminal, the cleft of the N terminal domain does not open and close. So this suggests that the dimer is in fact inactive. So this formation of the dimer seems to be a control mechanism. And this leads us to think about different kind of inhibitors in which we try and form the dimer through making molecules that cause the dimer formation. And that opens the way to a whole new class of blood pressure control drugs. Okay, we were able to publish our article in the EMBO journal, and we thank Diamond Light Source for access and support of the cryo-EM facilities at the UK National Electron Bioimaging Centre, EBIC. And this work was funded by the UK Global Challenge Research Fund. Start Synchrotron Techniques for African Research and Technology, which was that number. And we've written a website about the whole project, startproject.org. Now, the other contributor to the success of structural biology in University of Cape Town has been the Memorandum of Understanding between Instruct Eric and the university. This was signed in 2021 and enabled anyone from the university to respond to calls, attend meetings, and use the training facilities of Instruct. The grants from other sources funded travel and subsistence costs. 3 projects were completed with Instruct's help, using equipment and expertise that were not available in Africa. Well, the first one of these was the elucidation of the binding interface and active site of the novel ornithine acyl ACP and N-acyl transferase. And the relevance of this project is that it makes a potential biological detergent, biodegradable detergent, as a replacement for sodium dodecyl sulfate, which is the most commonly used detergent in toothpaste, hair shampoos, etc., etc. And what we were able to do is that it has 2 components, ACPP and OLSB. And ACPP we were able to crystallize quite readily, but we could make a lot of OLSB that was extremely soluble, but would not crystallize. So we were never able to actually visualize the crystal form of OLSB. And so we applied to INEX Discovery, which is part of Instruct, for access to an NMR, and we met with Hugo van Ingen, who then gave us access to the biomolecular research at Utrecht University, and we were able to use a 900 megahertz NMR machine. And we were able to predict the structure of OLSB with AlphaFold, and that enabled us to fit the peaks that we saw by NMR quite readily. And then we were able to see which peaks changed position when you formed the interaction between ACPP and OLSB. And we were able to then make a model of the complete enzyme. And that enabled us to then work towards getting a further understanding of optimizing this detergent production. The other project that we had was at Membrane Protein Laboratory in Harwell with Andrew Quigley and Peter Harrison, and Lenya Glimini stayed for 3 months in 2023 and was able to prepare and produce reconstructions of a number of thermostable mutations of the nitrulase fiber. And she was able to investigate the basis of the thermostability. In fact, we had access in that laboratory to equipment for actually measuring the thermostability, which we didn't have in South Africa. And we had access, obviously, to the Glasos and Cryos electron microscopes. And we were able to find, for example, in this particular example that I'm showing you, is that a mutation of this residue to an arginine produced an extremely stable interaction between two glutamates of aspartate, two glutamates and the arginine. And this enabled the enzyme it's at an interface, and the interface is then stabilized, and the whole enzyme becomes much more thermostable. Thermostability is relevant because the enzyme is used in industrial preparations to make amides and carboxylates from nitriles. And this is important in synthesis of drugs. The other project that we were able to do with Instruct Eric was also at Diamond, but at EBIC, and Vineshli Samuels was then able to go and use the Aculos microscope to make lamellae. It's a fib, actually, a fib milling machine, to make lamellae, which you could then examine in the Cryos, and she was able to get very beautiful tomograms of MTB, which still need to be fully analyzed. What we didn't anticipate is how difficult it was going to be to actually analyze these images. And the analysis that we've done at the moment is probably going to take a few more years. Okay, so back to the nitrulases. This is another nitrulase and I'm going to just discuss. This was done. This material was prepared by Eric Eppinger in Stuttgart, and we were able to image it using the Cryos microscope in Frankfurt. And what Eric did for his PhD was a massive amount of biochemical analysis of different substrates. Now, the enzyme itself converts a nitrile via a thioimidate, a tetrahedral intermediate, a thioester to finally make a carboxylate. And the R group can be many different things, and it's different things in different enzymes. So the basic active site consists of a cysteine, a lysine, and two carboxylates from glutamates, hydrogen bonded to the lysine, and then a water in this position. So you can see there's a hydrogen bond, there's a hydrogen bond, and then the hydrogen bonds to the water as well. And the substrate, well, we didn't really know where the substrate came in. And that's what I'm going to tell you now. So let me say that what we decided to do, having the knowledge that you get a covalent intermediate, was to model the covalent intermediate and then do detailed quantum mechanical modeling of the covalent intermediate, and then extrapolate backwards to where the substrate was positioned in order for the reaction to occur. So these are images of the covalently formed optimized structures based on the actual measured structure of the thioimidate and thioester, and then we extrapolate backwards to postulate that the substrate sits here. Now I'm going to say that this differs. Actually, this differs from what we predicted using this artificial intelligence-based program called Auto.Vina. And so that positions the substrate in a completely different position than we actually found. In fact, it's on the other side of the enzyme. You see here's the cis, and the cis is actually there in relation to the enzyme. So it's completely different. You can see there's the cis, and the nitrile is in front of it, and there's this assembly. Whereas actually what you have is that the nitrile pokes into the gap, and this whole assembly is on the same side as the nitrile. So then we modeled the substrate location based on the optimized structure of the intermediate, and then this enabled us to get some insight into the mechanism. And so here, what we're doing is making a video of how we think the mechanism occurs. So each one of these steps has been optimized in Gaussian, and so we have a quantum mechanically optimized view of the reaction coordinate of the enzyme occurring, and then we try to make an arrow diagram of what happens when this reaction occurs, and we've done it through the successive steps of the enzyme. Now I'm going to change direction a little bit now and talk about the work of Biostruct Africa, which I think is extremely significant. What Emmanuel and G decided to do was, in order to raise the interest of Africans in structural biology, he thought that he had to make it accessible. And obviously having this barrier of equipment in the way absolutely prohibited Africans from becoming involved in thinking about structural problems. And so he teamed with Google DeepMind, among other people, to run schools and courses which taught people how to use AlphaFold to predict protein structures and to use those predicted protein structures for useful drug design projects. And he formed Biostruct Africa, which is a company registered in, I think it's Ghana, Sweden, and Kenya, to do it. He decided to do it on the basis of a company rather than through an academic institution, which I thought was an extremely innovative and interesting idea. And it has been successful. So his first workshop took place in Douala in Cameroon, and what they did was there's Emmanuel with the people that were on the first course, and they conducted practical training in protein structure visualization, etc. And they used the tools, got people interested and excited and enthusiastic about doing structural biology. There were 20 participants on the first course. Then they had a second course at ILRI in Nairobi, in 2025. And there were 100 participants, and they expanded the scope quite significantly. They got a whole lot more sponsors on board, including Schrödinger, and they kept with Google DeepMind, and other various sponsors. And they were able to relate the use of AlphaFold to actual experimental technology, which was which they linked up with the Canadian light source. So they were able to do remote data collection, so they could show the people the whole value chain of structural biology. What has happened is, as a result of all of this, is a number of very interesting papers that have been written based on predicted structures and then artificial intelligence docking of various molecules into the active site of those predicted structures, and then trying to work out how drugs bound and how you could actually then optimize the production of various drugs for biological effect. And a paper that was written by Oludare Ogunyemi at the University of Ibadan in Nigeria is typical of the kind of papers that were produced as a result of these efforts. Now, I'm going to end up by saying there's no future without AI. And AI will accelerate and democratize structural biology in Africa, but it cannot and will not replace experimental structure determination. I've given you two examples of completely unanticipated results that came out of not AI. So the one was the dimer formation in the angiotensin converting enzyme, and the other was the location of the substrate in the nitrolases. So I'm going to say that Africa does not need a synchrotron for structure determination of biomolecules. So I think that we can do all the experimental work that we need to do with better, more effective, and much cheaper technologies. And one such technology is the modern diffractometer. An example of such a modern diffractometer is the Rigaku Extel Synergy S with a HiPix 6000 detector. This is an extremely effective photon counting detector, very, very fast, very sensitive, and produces actual beautiful X-ray structures very rapidly. And then the other technology that is absolutely groundbreaking and is now accessible to African labs because it's not that expensive is instruments like the Thermo Fisher Glacius 3 cryo-EM. And that's it without the covers on. And you can see that it's quite a beast, obviously complicated, but it has been designed in such a way that it doesn't require specialized buildings to house it. Now, the workflow with the diffractometer is almost exactly the same as you have with a synchrotron, except that there's no shipping step, so that you can get same-day results. And a modern diffractometer has been built in Istanbul, and it's called the Turkish light source, Turkish Delight, and it's built on the basis of one of these Rigaku machines. And there are the specs. It's got an ordinary rotating anode machine. There are several of these in South Africa, actually, the source. But what there are not in Africa are these advanced photon counting detectors. And so with the addition of the photon counting detector, and indeed the modernized geometry, and the very sophisticated software that has been developed by Rigaku, it becomes possible to do the whole of a protein structure in a time span that is completely reasonable. So you can get several drugs screened in a day. So the modern cryo-EM is an extremely versatile and effective tool. And it is probably the most versatile and effective tool for structural biology available today. So that's what a Glacios 3 looks like with its covers on. And the covers have been designed in such a way as to screen out the environment. So it's a completely environmentally isolated cabinet, anti-vibration, humidity controlled, magnetic field controlled. So all you need is that cabinet, and you can run the cryo-electron microscope. It's a tool with many uses. I've told you about the single particle work that we did on the ACE, but you can also use it for crystallography. So such an experiment is called serial ED, serial electron diffraction. And what you do is you try and grow crystals in the same way, but you then grind the crystals up into tiny little crystals, and you spread it on the electron microscope grid, which you then put in the electron microscope, and you scan the electron beam over the grid squares. And every time you hit a crystal, you get a diffraction pattern. And you collect one diffraction pattern from every crystal. You assume that the crystals are all in different orientations, and then you can index and scale the diffraction patterns from all of these different crystals. So you can have maybe 20,000, 50,000 crystals that you take diffraction patterns from, one diffraction pattern from each crystal, and that's your data collection. Then you data process it, and then you obviously do all of the processing, and then you can get a structure and you can refine it in the usual way. Now, it turns out that serial ED induces the lowest beam damage of all techniques, resulting in remarkable high-resolution structures. So in this dye-type peroxidase, an indicator of how much beam damage has been done is the distance between this water molecule and the center of the string. And you can see that in serial ED, it is the lowest. And then through various X-ray techniques to micro ED and other X-ray techniques, you get worse and worse structures. So the best structures by far are certainly from serial ED. And the reason for that is that you're only taking one exposure per crystal. So you can also use it obviously for looking at drugs. And what has been done is that you take your crystals, you put them on the grid, and then you put a droplet of your drug into the mix. And because the crystals are extremely small, the drug then penetrates the crystal very rapidly, and then you can see exactly where the drug is located in the enzyme in this case, very easily by solving the structures. So some conclusions. Acquiring and maintaining high-end equipment in Africa has proved problematic. Using resources abroad imposes additional hurdles and complications. And these hurdles are considerable. So anybody who wishes to actually ship crystals or electron microscope grids to a foreign facility will know exactly what I'm talking about. And you certainly can't do anything resembling a high throughput experiment by having to ship every sample and get an appointment on a foreign resource. So we do need to invest in equipment for structural biology, and we do need to cut our cloth according to our means, by which I mean we should buy these electron microscopes and X-ray diffractometers. So also a huge contribution has been made by AlphaFold and BioStruct Africa to make structural biology accessible to Africans at low cost. So people will be interested, people will be able to do experiments using structure predictions with AlphaFold, but ultimately things are going to have to be done experimentally as well. So care must be taken in interpreting computer-generated results, and machine learning for cryo-EM is absolutely essential. I don't believe that you can do a proper cryo-EM study without using machine learning. And in fact, Topaz has been integrated into all of the suites for cryo-EM analysis. So as things stand at the moment, structural biology in Africa is dependent on foreign funding, and this is something that we should all endeavor to change. So I think that the future lies in creating one or more centers which are similar in concept and scale to the Aaron Klug Center at UCT. And it's essential to consolidate and expand our international support network. Otherwise, we're never going to learn what people in the outside world are doing. And I think that we have to, a step towards becoming a member of Instruct ERIC is important. And I think that African countries must be made to understand the benefits of supporting structural biology, and they must deploy funds appropriately. That's really all I want to say. Okay, another last thing, an advert. So in the 19th to 23rd of September 2027, we're going to have a conference in Cape Town, which is a whole lot of different societies are supporting, but the main one is IU, International Union of Biochemistry and Molecular Biology. But even though IUPAP is having a conference in Berlin immediately before it, they are supporting African participation in this. Okay, so I think that's all I'm going to say. So I see Galileo is raising his hand. Okay, Lawrence, are you going to take it?
Are there any, thank you, Trevor. Any questions for the speaker? I see Galileo with his hand up already. Galileo, go ahead.
Yes. Listen, I appreciated very much the scientific part of your talk. I fully disagree with the conclusions you have drawn. I mean, the importance of structural biology is obvious. But when you say, and you put it in bold, that Africa does not need a synchrotron, in my view, with due respect, I think that it is missed the importance of having a structure like a synchrotron in Africa. Structural biology is not the only goal of that. First point. Second point, you are stressing the importance of foreign support, but everybody knows that in this moment the multilateralism is in big crisis. So I would say that what in my view is a better policy for Africa is completely different. Is perfectly well the importance of artificial intelligence, of what you are doing, and so on. But to put all the eggs in the basket of foreign support and so on, in my view, is a wrong policy for Africa. Thank you.
Okay, Canada, I'll immediately respond. I said structural biologists do not need a synchrotron. And I firmly believe that. I believe that all but very few of the structural biology experiments that need to be done urgently can be done with much cheaper equipment than a synchrotron. I didn't say that Africa didn't need a synchrotron. And indeed, as things stand, the differential between funding between the physical sciences and the
Actually, you
biological
wrote it. So, excuse me, Mr. Professor Sewell, you wrote it in bold. Africa does not need a synchrotron, and in
structural
the same
for
on the
structural
same
biology.
ground, you also said that you are using the Canadian synchrotron. So, I mean, the message may perhaps eventually the message was misunderstood. But it, in my view, is an important message that Africa needs strong structure. Anyway, I, I will not insist.
I did say that structural biologists, Africa does not need a synchrotron for structure determination of biomolecules. That's what I said. And at the moment, as things stand, um, the differential between the physical sciences and the biological sciences is about 40-fold in expenditures. So the biological sciences are a very poor cousin. And people are going to say, well, the biological sciences are too expensive, so we can't support them at all if we say that the biological sciences need a synchrotron. If we're trying to attract local funding, we've got to offer a cheaper option. And the cheaper option is these two devices that I'm showing you. They will do a lot of the job. And they will get young people interested, and they will perpetuate the initiative that has been started by BioStruct Africa to get people interested in structure determination. Yes, of course, we will use synchrotrons abroad. I think that there is absolutely no difficulty in getting time on synchrotrons abroad. The difficulty is actually getting the samples to those synchrotrons. So it's an amazingly complicated process if you have to pack up your crystals, ship them internationally, and then retrieve them. It's an unsurmountable obstacle. You might say, build a synchrotron in Africa, but that's a huge job. That's hundreds of times, thousands of times more difficult than shipping samples abroad. Whereas these two instruments are accessible. We can easily build and obtain and set up these instruments in Africa, and people can get to use them and experience the benefits of doing structural biology in Africa. That's what I wanted to say. That's my message. Okay, Paul. Paul?
Paul, go ahead.
Oh, yeah. Okay. Thank you so much, Trevor. In fact, it's always refreshing listening to you every time you give a talk. And, we've had various discussions, as regards the role of structural biology in Africa and how much work we can do using structural biology. And we've also collaborated in the past, when I was still at Zululand. So I guess we will still get to work together. Yeah, I just want to piggyback on what uh, Galileo just said just now. I guess it's a kind of like possibly maybe because I guess what you were talking about when you say Africa does not need a synchrotron for structural determination of molecules. And I think I get where you're coming from in the sense that let's face it, the funding is not there for us in Africa, really. I see when you look at Europe, when you look at Europe, look at other climes, even South America. Recently, we had this conference which was chaired by Lawrence, and I was amazed to even see countries from, part of South America, which basically you would think are not really are not rich, but also, doing something to host, maybe a light source and something like that there. Um, I think the problem which Trevor is trying to put out here really is the fact that the funding is never available. And when it's available, it is never enough. And in as much as we spend majority of our times, of our funding in Africa, funding various wars that doesn't make sense instead of investing into the future, of our young ones or of our future scientists, we basically don't have anything really to show. I can tell you, I really don't know where in Africa really that much money is being put into science really for almost everybody to use. I mean, South Africa is leading in that, in that wise. Other countries in Africa are also trying, but you expect much more, which we don't have. So I get possibly looking at the infrastructure, how much it will cost, and the fact that, we actually can access synchrotrons from other climes. Possibly that is why Trevor is saying for structural determination, we really don't need a synchrotron. But I guess we will need a synchrotron in Africa to do other things, like those in paleontology, they need synchrotron, the physicists, they need synchrotron to do a whole lot of things. But I quite agree because I've been using this strategy as well with my students, and it's been working fully well. But that does not mean that if the opportunity to have a synchrotron comes in Africa, we surely will not, will not take it. But I get what Trevor is saying, that we really don't need a synchrotron for structural determination of biomolecules. Another one thing I want to also point out is, in fact, this same slide which talks about the Rigaku Star Labs synergy. I mean, this is actually an eye-opener for me, and I would just want to know if Trevor can reflect properly on, especially the Rigaku Star Lab Synergy S. How much are we looking at in terms of rounds? Before we because I'm sure this is, even though you say it's a much cheaper technology, I'm sure it's not as cheap as we also thinking of that. The other part is the MOU, the interaction with Instruct Eric. Because to build, structural biology in Africa, like you say, we really need the collaboration with international partners. And I think Instruct Eric is one big partner which we can partner with in Africa. But I see UCT has an MOU with Instruct Eric. I would like to know the modality.
Is that the question?
I think he's frozen for the moment. I think he was saying about what is the modality of the collaboration.
Okay.
I think that's the best we can catch.
At the moment, it's the Instruct facilities are open to people from UCT, all of the things, but the money to fund that has to come from other sources. So we have to raise money from other sources in order to send the students to fund the travel and subsistence costs while they are using the Instruct laboratories. So the expertise and facilities of Instruct are free, but the travel and subsistence costs are for the University of Cape Town. What we've applied for is a Horizon grant that will now cover the cost of that travel and subsistence. So hopefully Europe wants to expand its influence abroad, especially in the field of structural biology, or especially in the field of infrastructure sharing. And they've offered, Horizon has offered, it's not very much. It's 8 million euros for this kind of expansion, and we've applied. Whether we'll be successful or not, I do not know. I think the case is quite good, but we will see. Andrea, do you want to ask a question?
Yeah, go ahead.
Sorry, audio. Sorry. No, more than asking a question, I wanted to add my thoughts to what you and Leo and Professor Paul were discussing about this. Africa does not need a synchrotron for structure determination of biomolecules. I am the scientific director at Sesame, and which is a synchrotron without a structural biology beamline, and our hands are quite full without that. So I tend to stay with you in affirming that in structural biology has for sure been extremely important in Europe, in UK especially, in USA, in Japan, in onsetting the present synchrotron radiation facilities. But I would suggest for those who are aiming at the African light source not to put it at the center of their narrative. Because, as you say, it is not the most important development that you can have. As Professor Paul said, paleontology, a tomography beamline, XRFs, fluorescence, powder diffraction, which are all much better in a synchrotron than in a laboratory. Those can give you a much better edge and a much better narration of the machine to be built. So not to point all or not to use the same amount of emphasis that has been given in the past for the construction of a synchrotron to structural biology. There are way many beamlines available in this moment. There are other methods. There is AlphaFold. There is the cryo-EM. This new cryo-EM with Glacius 3. There are fantastic laboratory machines available. So, and building a wider platform is more important than that.
Emmanuel, do you want to speak?
Emmanuel, yeah.
Yes. I just want to thank Trevor for your talk. It's nice to see how much you've contributed to structural biology in Africa. It's very, very inspiring. And also, I want to thank you for highlighting the work that I have been doing with my colleagues at BioStruct Africa. So I just want to comment also on what everyone has commented in terms of the fact that Africa does not need a synchrotron for structural determination of biomolecules. I think, in a sense, these are your opinion, right? And to some extent, I would say it's right and it's wrong. I mean, that's my own opinion. I will explain why I say so. When I was in Sweden, I used to work on membrane proteins, and when they crystallize, they are usually very tiny, like less than 10 microns, right? So the home source that we had, lots of people were working on soluble proteins, so they could collect data and solve their structure. So those people can say they don't need a synchrotron. For us, we couldn't use those home sources because it didn't work for us. We had to travel to the synchrotron where we have to use a microfocus beam to collect data on our crystals. But in a sense, why I see that your statement is right is because it's what everyone has probably alluded to, Like it's not the most immediate thing that we need to do, and because things are developing faster, so there are other better ways to do things. But in a sense that in Africa, if you were to have a synchrotron, traveling between countries will be more expensive than even traveling to diamond light source and collect data.
Yes.
So in a sense, why do I have to spend that amount of money building a synchrotron where I can spend less and go to diamond light source and collect the data? And if you want to sum up the expenses, let's say for a century, traveling to diamond light source will probably be less expensive than building a synchrotron. So that's how I see it, and that's my own opinion.
Yep, that's one of life's interesting ironies for sure.
Emmanuel, I want to ask a question. Have you spoken to the people that are doing serial ED at all? I mean, I think the promise of that technology, even for membrane proteins, is considerable.
Yeah, I totally agree. I totally agree.
Are there any other questions for this speaker or any other? Maybe I can ask one question and to Andrea, which you could just say, I choose not to answer this question at this time. And that is, are there any plans at Sesame to acquire a cryo-EM as like the other light sources basically use them as beam lines, like basically shared facilities? Is
Oh,
that
no,
something?
not at the moment. We don't have plans for that. So I would like first to see a community of with the need of cryo-EM to be really born around us. So no, not really.
Okay. Thank you for answering the question. I was going to let you off the hook by saying you could just choose not to answer the question, but
Yeah, no, it's okay. I mean, it's
okay. Are there any other questions? Then let's thank the speakers and all the questions and answers. I mean, this is a very robust discussion about this slide. I think I mean, I guess what we all know, the bottom line is that there's a technology revolution that's happened or still happening in structural biology that creates other alternatives. I mean, I guess in the 1990s, it was NMR. Now it's cryo-EM. But I'll put a pin in that right now. And if you come to the IUB-MB conference next year, we can all go out and have beers and discuss this. Trevor's buying.
It's a good subject. It's a good subject.
I'm buying them. Okay,
Nobody is right and nobody is wrong.
Yeah.
Right. Okay, well,
But
thank you, everyone.
everybody must be able to say their point of view.
Yeah,
Right.
Matt, do you want to speak
yeah.
again, or is that
There are
that
questions
hand?
in the comment.
Go ahead. So, this is really quick. Is that?
Are you reading the comments?
Oh, there was a question in the comment. What do you think about having 2 to 3 African centers of excellence? Yeah, I mean, actually, if I can say that is very consistent with the if you look up African light source strategic plans, strategic task force plans, I think there might be an article that talks about them. But it does talk about, what I think is called African Regional Infrastructure, ARI. And I think it's fair to say that cryo-EM centers can be these regional infrastructures that we talk about. I mean, there already is a second cryo-EM center in Africa that we'll get
It hasn't had electrons down the beam yet.
But yeah, it's kind of it's right in the commissioning phase. I guess is a fair.
Well,
statement.
it's a technician arrived from Japan to try and get it to work today.
Okay, so And we'll hear from that center soon. But that center, the beams don't go down nothing happens all by itself. You still need people. And so one of the problems that Trevor was saying, or the problems Trevor was saying, is that you got to have the human resources. You got to have the real intelligence instead of the artificial intelligence. So, all right, I'll put a pin in that too. And when maybe next year we can actually visit this new center. It's actually I guess outside of Pretoria, not Cape Town, but
Yeah.
okay.
Again,
No other questions. I will end today's session. Thank you, Trevor. Thank you, everyone.
thank you, Lawrence. Thank you, everybody. Thanks for coming.
Thanks, Trevor. Cheers.
Cheers.
Thanks, Paul.
Bye.